This lecture is called the ABCs, but the second part is more like D, E, F, all the way through to Z. There's quite a lot of technical content in this. We'll try and get through as much as we can. I'll make it, I'm open to questions, so please feel free to ask if anything is too confusing. Happy to help out, okay? Otherwise, if you don't want to interrupt, also happy to respond to emails after the fact. Feel free to shoot me an email out. Similarly, if you want to help yourself to food and drinks halfway through the lecture, absolutely fine. I'm not offended. Please feel free. So let's begin. Today we're going to be talking about a lot of what we covered yesterday, but in more depth. So you will see some slides that you recognize from yesterday if you attended, and this is going to be covering some of the, for example, the learning types in more depth. That's the supervised, the unsupervised, the semi-supervised, and reinforcement learning. Data, including test validation and training data. We're going to go a bit more depth into what deep learning is. If you remember that sort of structured tier list that we had of artificial intelligence at the very top, then we had machine learning, then we had deep learning, then we had generative AI at the bottom. We're going to talk a little bit more about deep learning to provide us more depth to talk about generative AI. Then we'll talk about how generative AI works in, again, more depth. Well, yesterday we had an introductory look over of how an LLM works, a large language model. We're going to go into more depth with that and also then mention GANs, which are used for, among other things, image production. Then we're going to talk a little bit of generative AI in research and how it can be used for those interested in conducting research with generative AI. And at the request of Rob, I added in a number of social science examples in there as well. And then we'll conclude and go over everything to make sure it all makes some sense. So, supervised, unsupervised, semi-supervised, and reinforcement learning. You'll recall this plot from yesterday. So we have supervised learning, which is effectively you have data plus labels. You have unsupervised learning, which is just the data, and you have reinforcement learning, which has neither of these things, and it's just an agent in an environment exploring the environment. For example, a robot exploring a maze. So let's go into some more depth with this. Supervised learning requires the labeled data. The purpose of supervised learning is this idea of prediction. You want to create a model that, given a new input, can accurately predict the output or the class to which the new input belongs. There's a specific type of training related with supervised, which is during the training phase, the model's fed with input data and the correct output. The model learns to associate the inputs with the correct outputs, the labeled data. We have what's called an error measurement. So because supervised learning is effectively predicting certain things, and it can actually be judged and evaluated as to how good those predictions are. And this is done by an error measurement. Not how good is it, but how wrong is it, right? That's the error. And this is done through a cost function. And then there's also the model adjustment. Based on this error, the algorithm will then adjust its internal parameters to minimize the error in the future, so it won't encounter the same problems again and again. Supervised learning can be used in social science to predict election results, on historical voting data, current socioeconomic indicators, used to analyze and predict trends in societal behaviors, such as the prevalence of certain social issues based on variables like income. These are the kind of things you can provide labeled examples to in order for it to learn, because you can say, this is what the data looks like, here's what you're supposed to predict, and it learns from this information repeatedly. So here's our plots sort of showing this. So we have our labeled data, which is going to be pictures of some vegetables, and then we have labels explaining that that's a carrot, tomato, and pepper. We pass that into the training. It predicts certain things, repeatedly we keep saying, how accurate is that? If it does a good job of it, we say great. If it did a bad job, we say not so good, try again. And we keep telling it what's right and what's wrong. And it updates these values internally so that it can improve its estimations, its predictions. Simple as that. That's supervised learning.
So Ken, let me try to get I'll give an example. You tell me if I've got this right. So for instance, we might be really interested, because we run a survey company, we might be really interested in knowing who's going to vote and who's not. So we'll have some data sets available to us in which a person is indicated, that's the labeling, indicated as having voted or not voted. Mm-hmm. And then we'll know a pile of characteristics about each of these folks, a bunch of different variables, covariates about them. We feed it into the supervised learning machine, and it offers us back a model for predicting whether a person is going to vote or not.
Exactly. And early in the training, the model might be quite inaccurate. So you try again and again and again, and eventually we'll get better and better at it. Okay, that's supervised. Unsupervised learning, there are no labels. We're just passing in raw data. This could be, for example, text or pixel data, whatever it is. Doesn't really matter with input types. Able then discover some kind of structure within that data. So, for example, it seems like there's a lot of red in this section, or that if you have data points on X and Y axis, they can identify, clusters or various things like this. It's a bit of structural discovery. There's also what unsupervised learning is a specialty, and is not just the clustering, but also dimensionality reduction as well. So, for example, principal component analysis is very akin to this, where you can pass it a set of data, it'll find the most interesting intrinsic parts of the data that represent the idea of that data, and it'll start being able to remove the other parts of it. So what are the core key elements? If you think of this as a picture, do you need to store every pixel value? Not necessarily. You can probably store the general ideas, the sort of lines where the drawing of an image in Microsoft Paint is. You don't need to save 99% white pixels, right? If you have a simple drawing, you can just save that simple drawing, right? And it'll massively reduce the amount of space. Training as well. In the training phase, it's exposed to raw data and tries to automatically find patterns and relationships. It's particularly useful in exploratory analysis. Like sometimes even when you want to use supervised learning, but you want to have a better idea of what the structure of the actual data you're using is first, you might want to do unsupervised before you do supervised learning. So you can have an idea of what the internal structure is. Again, in social sciences, we could identify hidden patterns or groupings in complex social data, such as clustering. So again, we're talking about voting patterns. We could cluster certain groups based on other data points. So for example, can we correlate political opinions on a specific legislative issue based on income levels? Right? That's the kind of clustering it can do, and it will identify without any further information. You don't need to label it and provide any additional information. It just sees that this group tends to have a structure. That's all it'll see. That's kind of what it looks like. So you pass in this raw data, and it can regress, or it can classify, or it can do dimensionality reduction, and so on. It just looks at the data and identifies patterns. No labeling required. Okay, we didn't really mention this yesterday. Semi-supervised learning. You can already kind of guess what this is, right? The general premise is that you have some data. A large amount of it might be unlabeled. We have a small amount that is labeled. For example, a lot of research has this because it's expensive to label data. If you have, I had one student I worked with at Michigan State who had, I think, something like 10,000 hours of pig video of a pig in a trough, right? Multiple pigs, and he was trying to measure how aggressive these pigs were. And they had certain behaviors he looked for. So, if one pig would mount the other, or would bite its ear, or pull its tail, or nudge it, or whatever. And if you're trying to train a model to detect these things automatically, you need to provide it labeled data. So he sat for thousands of hours watching these pig videos over and over in 10-second chunks and saying, aggressive behavior this, aggressive behavior that, right? Repeatedly again and again. Semi-supervised in this instance would be, you take maybe 10% of the data, you label that manually, and you let it teach itself to label the rest. That's kind of what semi-supervised learning can do. It saves a lot of time and effort and literal cost, because it costs real working employee hours to label data, right? Generally. There's more information in the slides if you want to look through them. And some examples at the bottom. So if you had a small set of a large set of unlabeled data, a small set of labeled data for public opinion about your policy initiative, you could have it so that some of that information is thoroughly categorized, some of it is not, and you can sort of assume the rest. These models actually have very nice outputs compared to just pure unsupervised. Ideally, you'd have the whole thing labeled, but semi-supervised is a great middle ground between the two. You can kind of imagine what this looks like. If we're trying to identify these fruits this time. We have a small amount of labeled data. We have some data we want to predict that hasn't been labeled. We pass this all in, and it learns from the labeled data sets to label the unlabeled data, and it can then start learning from there and detect whether the items are apples or pineapples. Sorry, apples and pineapples. Reinforcement learning, we mentioned this as well, is the agent is consistently and forevermore learning based on the new encounters it comes across in the environment. So unlike supervised, semi-supervised, and unsupervised, where you train your model and then you cut it off and you say, you're done. You're now a model that we ask questions of, you're no longer learning. Reinforcement learning is something that continually learns forevermore. This is good and bad because it's often a very expensive process, but it also means that it can continually learn. That means that if there's new environmental changes that were unexpected, it can hopefully adapt to them. However, they are very expensive. So the agent and environment, I've already sort of explained. The reward system is where the objective is to learn a specific policy, a set of rules that it will adopt based on the environment. So as the agent traverses through the maze, for example, it will be continually told that's right, that's wrong, based on the environment, what it's doing. Again, if you're trying to traverse a maze, distance from the exit might be a good way of evaluating fitness, right? So you can say, if it starts taking actions that frequently lead it away from the exit, you continually say that's not so great. That's assuming you know the answer. Instead, you could say, if you didn't know where the exit is, you could instead say, you want to have a nice mix between exploration and exploitation. So you'll sometimes go lots of random directions. Sometimes you'll use knowledge you had in the past and create a policy like that. Delayed rewards as well. So quite a common problem in early reinforcement learning was that you would provide these awards or these punishments based on the agent's actions. But if you had some reward, there was a delayed gratification. Sorry. This is the kind of thing you actually see in humans and animals as well. If you're training a dog, you find that if you reward the dog too frequently and too much, it'll get too excited and it'll no longer actually care about learning the task, right? Humans are the same, of course. Same with these algorithms. We have to actually start having delayed gratification built into it so that it learns that sometimes going through bad parts means that we get to the better parts, right? No supervision is required, so we don't need to provide labeled data sets or anything like this. It just learns from the consequences of its actions, which also means it's expensive because it's constantly learning. Supervised, unsupervised, and semi-supervised are expensive at first, but then you have a model that's quite efficient at the end, and it just works. Whereas reinforcement learning is continually learning, so it's a costly thing. I was actually really interested in the kind of applications we could have for social sciences with reinforcement learning, because you tend to think of video games as the default, and how does that work with this? But it does make sense. If you think of a politician who is continually learning about legislation that they should put in place, and they get response from voters or from sponsors that are funding their campaigns and such, they are actually doing a sort of reinforcement learning. They're continually trying to work out what the best approach is and what they should do next. So you can actually have a sort of reinforcement learner act as almost a politician, or to simulate it, which is really interesting.
There's a question here.
Yes.
How can there be consequences if it's unsupervised? How does that work? I think this is related to the question I had. Does the user have to program the reward function or something for the explorer to learn from?
That's a good question. A lot of these problems that we're trying to solve, we sort of think of them as you know it when you see it. Like a good solution, when you know it when you see it, but it's hard to describe. That's kind of where reinforcement falls into. There are a lot of problems where if you just know the answer, why are you trying to provide a solver, right? If you just know the answer, so if you have an evaluation function that says this is the correct answer, there's no need to have an artificial intelligence. So instead, you have to program the environment itself to give specific responses based on. So instead, it's like the example I gave earlier. Instead of trying to find the exit in a maze, you try to have some other kind of evaluation metric that says there are some. Maze is probably that example for this. Say you're going through a maze and you had to come across certain keys to unlock certain doors. You'd have smaller rewards along the way that can represent goodness. And the same thing can be applied with larger, more realistic problems as well. You have smaller evaluations and smaller, but effectively it's the environment itself that rewards and punishes the agent.
So I'll follow up with that. So So I'm thinking like agent-based modeling that I know, for instance, we might have a set of parties looking for where to locate their platforms in like a social and an economic two-dimensional space. And they're going, and what the researcher is going to do is set up the function that rewards these parties with votes based on where they locate, where the people are, and where the other parties locate. And the surface is invisible to them, so they don't know where to go to maximize their votes. So they're going to kind of explore around. But it, in this case that I'm describing, this is like the work of Coleman, Miller, Page. It's the researchers who have to set up that reward function, right? Like you design the reward function that the agents get, the computer agents get for taking certain steps and actions. Is it like that?
Yeah, it's very much like that. And I keep using the word environment, because maybe I'll throw this slide up so maybe helpful with this explanation. I keep using the word environment because it truly is actually the environment that provides the rewards to the agent, literally. And this is, yeah, when you use your example, there are means of evaluating progress without necessarily knowing the answer. And again, that can be voter satisfaction. Right. It doesn't mean that you know what to do in order to provide voter satisfaction, but that evaluation metric is still completely valid. Right. And that's kind of how it works. You don't need to know the answer to be able to evaluate. Well, you see, you know it when you see it. Right. Okay, so this is a sort of brief introduction to how reinforcement learning works here. So we, in the middle, have this sort of floating policy. This is the rules that the agent is going to follow. This is the thing they'll continually modify based on the rewards provided by the environment to the agent based on what it does. So every step that the agent takes, every action it takes, everything it decides to do, it will then either provide a reward or not, or a negative reward or punishment, if you like. And there's a whole slew of research on how to best do that sort of reward punishment cycle. I should also mention that reinforcement learning is actually one of the oldest forms of artificial intelligence. Some of the people who actually coined the phrases of machine learning and such came up with reinforcement learning as the first AI. So it's quite interesting. But I hope you also see the fascinating point of artificial intelligence is generally just intelligence that can be seen within a computer. It can be programmed or not. Machine learning tends to be more autonomous. Right? Deep learning has more to do with these multiple layers and mimicking the animal's brain. But reinforcement learning is actually more like observing a living agent in an environment in the real world, like an animal or a plant, and seeing how it acts. Those rewards might be food. Those that's what FIBA was based on, is observing real living organisms and how they move towards rewards. So these are the 4 types of learning. There's supervised, unsupervised, semi-supervised, and reinforcement. There are some examples at the bottom if you want to look at more particulars, because these all are fields, right? Fields of algorithms. Feel free to look into each of those later. So how do you choose the right method? It really depends on what you're trying to do. So if you're using supervised learning, it means you have a considerable amount of labeled data available. That's the first thing, right? If you have the ability, the cost, and so on to be able to produce this, then you want to use supervised. Use unsupervised, you have a lot of data, but it's not labeled, and it's used mostly for clustering, anomaly detection, dimensionality reduction, looking at patterns in the data. Whereas supervised learning is more for classification, regression tasks, predicting customer churn, for example, based on usage data. Reinforcement learning is when the problem involves sequential decision making, right? What do I do next? The data does not need to be labeled, of course. The only feedbacks in terms of rewards or penalties. It's used for control tasks, game playing, and areas that need for adaptive real-time decision making, like robotics or policy refinement. Then semi-supervised is somewhere between the top two. You have a small amount of labeled data, and you have a lot of unlabeled data. Data availability as well. Computational resources. Reinforcement learning, like I mentioned before, is very computationally inefficient, but if you need that adaptiveness, then it's a good choice. But generally speaking, the choice isn't always clear-cut. It's not so obvious, and perhaps some initial exploration, preliminary experimentation is required. Because these things are expensive. I used to work in genomic prediction, and I know very well that, it's very easy to say, oh, I think I got the algorithm working. I'm just going to hit go on the experiment on the large data set. And then you realize it takes 2 weeks to run, and you think, oh, that's fine. I can run them in parallel, and I'll have lots of them running. And then you realize that you've run up a carbon bill that is more than you would have done in your life. That's not a good thing, right? These are incredibly damaging to the environments, so the environments around the world. So you have to make sure that when you are designing experiments or playing with these algorithms, that you're going to try on a small subset of the data before you try running on the entire thing, because you want to make sure that it works first time, right? Speaking of data, all of these different types of machine learning, deep learning, algorithms, and all these different types of learning methods all require some kind of data. So what we have is, for example, I say all data available, right? So this could be thousands of X-rays, or all the papers on archive, or all the code on GitHub, all the audio on SoundCloud, whatever your database says, doesn't matter. There's 100%, right? You then need to split it up, because any scientific test that you do requires testing and validation, right? That's a basic requirement of scientific rigor. It's the same with these kind of things. So you have your training data, which is how the model first learns. It tries to learn over and over and over again on this data set. This is kind of that supervised learning. You let it repeatedly check itself. Is this correct, or is it wrong? Is it right? Or if it's unsupervised, that also works as well. Just try again and again and see how it goes. Validation data is where we have an unbiased evaluation of the model and the data. So you notice this is a separate segment, right? It is completely separate. So it's trained over here, and then once it's being as it's being trained, it can use the validation data to make sure that it's tuning its hyperparameters correctly, which is hyperparameters are basically just the rules that are in place for running an algorithm. So to prevent overfitting, you have this testing against this frequently and making sure that what you're doing is going to keep working. And you have the test data as well, which is a separate segment again that provides an unbiased evaluation of the final model. So you've run this all the way through. You've got your, you think you've done a great job. You think it's learned the original corpus of information, and then you want to actually test it on something separately at the very end. This will give you an actual evaluation metric. So if you have some number that says this is 70% accurate, when you're looking at the internal data sets, when you test on an external data set, you'll know for sure if it works or not. The best example of this is if you have a car, for example, and you have a very small, very smooth road outside, and you're testing your car that you just built on this road, and it works really well. It's a perfectly flat road. That's nice and all. You need to go try it on some hills. You need to go try it on different terrain, right? You need to test it on different data sets in order to ensure that it works in something that you haven't been trained on. That's a sort of generalizability to that problem. This doesn't mean you're trying to train your AI to work on absolutely any problem in the world. It's still within the thing you're trying to work with, right? But this is how you make sure that it is generalizable to other of the same types of data. Okay, some more depth into deep learning. So machine learning algorithms are very, very, very good at pattern recognition. Machine learning is all about finding patterns and making the connections in the data. For example, a machine learning model could learn data about house prices in Ann Arbor, and that's not just expensive, right? It can do it based on, for example, the size of a house. So it could say square footage is somewhat correlated with how expensive a house is, right? Which makes sense. So neural networks are a type of machine learning where the information moves in from the input layer through any number of hidden layers to an output layer. The word deep in deep learning comes from the number of layers. So neural networks have existed for a long time. These are not a new concept. But the whole deep learning part of it is where we have the computational resources available to actually do this. So they look like this. We have the inputs. This could be, for example, an image that's segmented into pixels or whatever. You could have a book that's handed in that's broken up into words or letters or sentences, whatever. And your output layer, again, it very much depends on what you're doing. If you're doing images, it could again be pixels, it could be whatever you're looking for. But generally speaking, with deep learning, you're trying to get some kind of answer out, like a regression model or something. So this output layer would be potentially some sort of number. Like this is how good we think we can fit the data, for example. So let's start delving into deep learning. Learning occurs by adjusting the weights between the nodes in response to the errors made. I've said that before, right? So it tries to learn something, it predicts something. If that's accurate or not, we'll find out by the evaluation, and then it will adjust its weights accordingly. So it'll find out over time, it'll get better and better at predicting or doing whatever it's doing. So this is a neuron, and that's obviously based on the brain. We have our inputs as we saw before, that's them here, and we have these weights here. These are the things that will be adjusted in order to decide whether what features are the most important in a data set that can judge something accurately. Here we have our summation, which we'll get into a little bit of details exactly why we do that in a moment. Same with the activation function. So you know how in the human body, for example, we're constantly feeling things from neurons all around our body, right? We're able to feel temperature, we're able to feel pressure. Technically, you can feel your socks and shoes on right now, but you're not thinking about it. Why not? It's because there's a system in place where your neurons activate based on certain thresholds, right? And one of those thresholds is for pain, for example. If it gets too warm, that'll take the forefront of your consciousness. It's very similar to how we've designed neural nets. So these individual neurons that we're now seeing here will activate depending on how much of a priority they have, right? And this can be changed through their weightings and such. We'll go into more detail. Okay, so let's have an example. We're trying to predict house prices based on square footage, like I said. So we've got the living area, feet squared, and here we've got a price in thousands of dollars. So our weights are initialized randomly. It doesn't matter what they are. We can choose any number between 0 and 1, that'll be fine. We input our square footage here. So we say 2,000 square feet. And we're going to try to guesstimate how much that's going to be worth, right? We have this thing called bias. This acts as a sort of additional input that always has the value of 1. This makes sure that we can improve the flexibility of the model. We'll get into more detail about this, what this means in a second. And then the very end of this calculation. And all it does is it takes this input, it multiplies it by the weight, it adds the 1, and our answer is 601. Right. Fair enough. Doesn't actually seem that complex when you see this horrible diagram before. That's effectively what it does. Okay. This is then handed over to the activation function. So that's this part here, handed over to the activation function. So the activation function will introduce non-linearity into the model. Problems can arise if we have linearity, right? This is essential because without it, no matter how many layers we have in our deep network, it would still behave like a single layer model due to the linearity. It becomes a linear function. So there are dozens of activation functions that exist out there in the world. We're going to use ReLU. This is rectified linear unit. That is a terrifying name, but it's actually quite a simple thing. So here we have an actual price of 500,000, a predicted price of 601, right? Will go off. We have what's called a loss function here. This is how we start thinking about the evaluation, right? How well we did. This is calculated through, depending on which one you select, but in this case, we're going to use mean squared error. So this is pretty common for regression type problems. And this is, again, quite simple. We're just saying our actual value, which is this 500,000, minus the predicted value, 601, we square it. So that's this summation here. And needless to say, our original estimate was about 150 years out of date, right? You can't get houses for that price. So we need to go back now. Our initial guess was horrible. So we need to go back and update our weights each epoch, which means iteration. Each time we try, we need to go back and update our weights to say, you're really far off. Let's change them massively. Okay. And that's how a neuron works. You have your inputs, so your bias and summation of your various inputs that are weighted, and then you put them through some kind of activation function, which depends on the kind of problem you're trying to solve, and which one you select is very much a science in itself, and that takes a lot of time to decide. And then you output.
So, Ken, we have another question. And that's a good slide to leave it on. The questions are two that are offered here, and I'll do my usual thing and add a third to it. The question is, when do we use neural network or deep learning? When would we use it to make predictions? and how do we determine what activation function to use? And I'll just elaborate on this a bit. So as you described it in your very, very simplified, I recognize, example, it sounds like numerical optimization, right, for a regression problem. So yes. we set up a loss function, which is sum of squared errors. We take initial guesses of weights or coefficients on the x's. We add up weights times coefficients. That makes a prediction. We get an error. We sum the squares. If the error is really big, maybe we tweak the coefficient guesses and go in a different direction. So the new item, perhaps new item, is the activation function. So if I thought of that as the as you start with a linear additive argument, right? The x beta part, where we just guessed all these coefficients. Then you're going to transform x beta by, say, maybe, I don't know, a logistic function or something like that. Talk to us about that activation function. Do we, is it literally like, let me throw a sigmoidal function at it because I think this outcome is sigmoidal, or let me choose this other function, or actually are we searching across functions as well? Help us out with that part.
That's an excellent question. And I think you answered a lot of the question that was asked in the chat there for me, actually, which I very much appreciate. I've got another slide deck here that really goes into a lot of detail about the activation functions. And I don't want to go into a lot of detail. I do want to just highlight that they have different purposes. Let me find this very quickly here, if I can. But effectively, selecting your activation function is dependent on the task at hand. So, for example, if you're handed in a value that is negative and you don't want a negative value, the one we're using right now is ReLU, which is the rectified function. And what this does is it's really simple. You have we use R, right, or Python. We're trying to have a maximization between 0 or what's handed in. In other words, we're going to make it positive, whatever it is, or 0. And as simple as that. Activation functions are used depending on what your purpose is and what you're trying to achieve on your current layer. And we'll get into more details about why we do that with specific layers soon. But the activation function is really there to just make sure that we have that non-linearity more than anything. That's the whole purpose of it. And there are dozens of types of potential activation functions you can select from. So I tried to really search another slide deck to find the example that I could show you of these 9 different ones I had there.
Well, I also don't want to sidetrack you too long, but it sounds like you could also search across activation functions as well. Right?
Oh, yes. Selecting the correct activation function is a science in itself. It really is. Same with anything here. Finding ways to select your weights, finding the correct way to do the number of neurons, the number of layers, which activation function, all of these things are a big part of the science of doing deep learning, and why you can't just say, I do deep learning, right? A goal. You need to actually think about and try and test various different parameters to see what suits your problem best. I think this will be explained a little more when we get to the layer section as to why we do these things. Okay, I know it's a lot of information to handle. So backpropagation is this. We said that before. We have this. We get through to the very end here, and we have this value that tells us our goodness, right, our quality, and we saw that our initial estimate was really far off. So what we have here is we're kind of trying to do a minimization here, right? We're trying to get to this minimum point down here where our error is as small as possible. That's all we're really trying to do, is minimize our error, and we can do this pretty simply, right? Through a mechanism called backpropagation, we're trying to get this error and pass it back through the network, calculating the gradients of error with respect to the weights and biases. These gradients point in the direction of the steepest descent in the error space. So we use these gradients to adjust the weights and biases to minimize this error. In other words, every time we have an error, we can say, that's bad, let's reduce that somehow. And this is literally what it does. It just minimizes this value to get to the bottom. Okay? That's effectively what we're doing here. We update those weights because we know our value on the other side is bad. In this example, we're doing a supervised learning problem. So we have the house prices versus footage. So we can see the correct answers, right? We have these available answers. We can say that, well, we know that this value is actually like this. We know that it costs this much for a house with this much square footage. So why are you estimating millions difference? Right? Okay, so neural networks. The weights and biases are updated on a learning rate. That learning rate is a number that is, again, is a science in itself deciding this learning rate. But effectively, you want to be able to explore the search space a lot early on, and then you want to really exploit later on. So you're trying to jump around a lot as much as you can early on to try and to get to the right ballpark. Then you hone into the correct solution. So in the case with this, you might start up here. You don't want to move down a tiny little half point. You want to jump over here, or maybe down there, and then slowly you might bounce around closer and closer and closer, and then you sort of climb down. You kind of see this here actually, how the points get smaller and the range between them gets smaller each time. So that's what our learning rate's for. That's what this parameter here is for. It's very key, and that can be adjusted and changed as it runs. So we have our old way here that's passed in, it was 0.3. So we're going to make a new way. We're going to take 0.3, and we're going to say that the weights and biases are going to be based on this learning rate. So the new way is going to be equal to the old weight minus n learning rate, right, times the gradient we were looking at before. Okay, doesn't matter what the numbers actually say, but that's the idea, the gradient. And so we have this number that comes out here, minus 499.7, right? So our original weight was really far off. Okay, then the biases are going to be updated in a similar manner. So what we're going to do is say the old bias minus n again times the gradient. And that's how we update our biases. And that's how the neurons are going to be updated repeatedly so that they have a better idea of how to hone into those specific answers. Okay? It's not very different from linear regression in this sense, except that there's this learning factor on top. So deep learning is this subset of machine learning that we talked about. It learns complex patterns from large amounts of data, and these layers of artificial neurons or nodes work together to extract meaningful features. For example, handwriting recognition. So these are the individual neurons we're thinking about, right? These on here. And we have our input, we have our output. Okay. So what are these layers? These layers extract different features from the input data. For handwriting recognition, as the example from earlier, the first layers might identify edges, while deeper layers might find more complex shapes or objects. So again, if you're doing facial recognition, you don't want to just look at a single pixel value and say that's a rather light shade or a dark shade or whatever. You want it to be able to consider neighboring components, right? And that's how it's going to detect shapes or patterns or lines in an image. And this happens by using these multiple layers. So having multiple layers allows them to, and with this connectivity, they manage to consider nearby other pixel values. Not necessarily just pixels, but they start becoming more abstract. The more layers we have, we can say this represents the shape of a chin, perhaps. But this is not manually coded. We don't go in and say, oh, node 4,000,007 is going to equal the nostril, right? Instead, this is done automatically through this process of weight backpropagation. Right? That's how it does it. It's kind of magical, right? They can do this by itself. So is generative AI the same as deep learning? We talked about this yesterday, so I'm not going to go into a lot. Generally speaking, Gen AI is a subset of deep learning. We have a lot of differences, including how the evaluation functions are done. The underlying technical architecture is different. And Gen AI generates content, whereas deep learning is more for extracting some pattern recognition or some regression. You're trying to do some sort of analysis generally. And deep learning is used for discriminative tasks, like classifying images. Okay. So let's go into more depth with generative AI. Gen AI, like the transformer, which you think of GPT, the T in GPT, ChatGPT stands for transformer. Right? Transformer is a deep learning model introduced in 2017, and it's used in the field of natural language processing. This is the paper that is the paper of everything nowadays. Attention is all you need is so very important. If you ever want to read some scientific literature on this, that's where you start. This achieved state-of-the-art results on many natural language processing problems that existed before that. This blew everything out of the water. It's a fantastic paper. For example, when training the entirety of Wikipedia, transfer model could generate text that mimics the style and content found in Wikipedia. We see this now as common knowledge of ChatGPT and such. Back then in 2017, this was amazing. So the word attention is really important here. The transformer model is designed around this attention mechanism. And there's this special mechanism called scaled dot product attention. This mechanism is really important because it allows the model to understand the context of different elements in a sequence by assigning different weights to different elements. So, very simple example, the cat sat on the mat. Cat and mat are more important, right? The is probably a very unimportant word in that sentence. That's literally what this means, okay? Attention weights are just trying to apply importance to words. So here, for example, we have the handed in, mat handed in, and what we're trying to say is, can we get a dot product weighted sum here? We got a attention score based on these of 3.1. We're not going to go down to the maths, especially with the time we have. We apply some kind of function here. We're going to use softmax, and we get this output score of mat, right? So this is how we're going to be calculating the scaled dot product attention. In practice, transformers use something called multi-headed attention. So it has several like parallel attention layers or heads. This allows it to focus on different parts of the input simultaneously. So it's not just looking at one single word at a time and then working from there. It's actually looking at multiple words all at once at the same time. Multi-attention, right? For example, one head might actually focus on a specific word, whereas another head might actually focus on the syntactical information behind it. Remember, yesterday we talked about context as a very important part of how the learning process in these models are. This is what I was hinting at, is that you can actually have these specific mechanisms that will, some of which can focus on specific words, some can focus on the contextual meaning behind it at the same time in a parallel fashion. Again, humans do this. When you hear sentences, you're not just thinking about the individual words one by one. You're not just thinking about the key words that are important. You're giving your attention to the meaning and the context behind all of those things together, and you have some kind of output. If somebody speaks to you for an hour, like myself, what you walk away with is kind of like this, right? You're extracting these key features that are important based on your previous training data set, and that's what this does. So we're going to briefly touch on this architecture as well. So we have this input of the cat sat on the transformer model will consist of an encoder and a decoder. And in the middle, we have these contextual embeddings. So the encoder is going to read and process the input data like this, or a Wikipedia sentence or whatever. The decoder is going to generate the output data, for example, the next word or sentence in the Wikipedia article. And then here's where the magic happens, that contextual embedding, the meaning behind it. So inside the encoder, we have this input that comes in, for the cat sat on the, it's passed to the encoder. It looks through these embeddings and positional encodings. So we have the order, we have the meaning behind it. It passes through these encoding layers that will, however many there are. And then we have the decoder, which will look at these embeddings from before, go through the multiple layers, and then output something. So you know how I said yesterday that these layers have this sort of embedding and the decoding where it transforms these into numbers and these vectors that mean something in an embedded fashion. This is where we're sort of seeing this happen, and how we have the contextual embeddings using this mechanism that can extract real meaning from these phrases and these contexts. The position of the words is also super important. So this is the positional encoding. We have words like the, and the position being in the fifth in the sentence. These are combined together so that so that you can actually have the context of the meaning in the sentence, not just the word itself. That's how it actually mathematically does the calculation. How important is this word based on the sequence of characters and words and sentences and paragraphs and texts that are passed in. So the transformer is trained end to end. This is how we have the input here. We have a transformer here. We have some kind of optimizer over here. It's going to update the weights repeatedly as it goes through. It'll start predicting the words. We'll have the loss function. This is very similar to what we saw before in deep learning and why we went into some detail with that. We have these loss functions. They're going to, our cost function, there is going to be telling you how good or how bad it is. And it's going to continually pass back the information to the optimizer, which will update the weights for the transformer. So when you have something like ChatGPT that is learning repeatedly on a training data set, this is how it does it. It's kind of inspired by that deep learning model of being able to be continually updated based on what you find and the more information that you come across. So then we have the actual new word being passed in, right? It tries to predict new words, and that's how it learns. That's the function of learning. It's effectively saying, we have the answer, but what would you have done? And we can compare the answers. And that's how it learns over time to update these values so that the transformer becomes more impressive. So the cat sat on the word mat would be the ideal next one. And over time, it will learn that that's the likely thing we said, just like how humans do it, right? So these function just like neural nets as well. They use backpropagation to update the weights in the model, incrementally improving the model's performance over time.
We have a couple of questions right here. So, so one is this training how plagiarism detection programs can determine that the document does not belong to a particular student? In other words, the program has learned what the student is likely to write, and so if that is not written, then it's cheating.
That's exactly how it works. Yep.
And then another question, which is, are you saying that GPT is retraining in real time as it's going along?
No, this is how it was trained in the first place. That would mean that ChatGPT is almost like a reinforcement learner, where so what you input into exists in a session, it does not store that back into the data set immediately. Not yet, anyway.
So, okay, I'm going to use my chair's discretion, which I've been using repeatedly throughout. So I found myself wondering. People often say my writing has too many interruptions in it, that I stop and parenthetical here and a pause and this. So it's unlike how other people write, apparently. So I'm told.
Good.
What does how does the model deal with that? That ordinarily a certain sequence, a certain contextual embedding would signal one thing, but different people have different writing styles, so it would be different. It's averaging across a billion writers or something.
This is a really interesting question, because it kind of gets into the how you can actually prompt models to write like something, right? You can say write like Albert Einstein, right? And it does that because it's then just focusing on that trained data set of that person. But if you just ask it generally, it actually has some initial pre-prompts that's provided by OpenAI or Google or whoever owns the model or whoever created the model. That will give it some initial instructions, like you will be a responsive and helpful chatbot to whoever asks you questions. So that's the default. So whenever you ask questions, that's the reason it's so polite and kind, and that's because it's actually been pre-prompted to do that for you. And so it's not actually part of the training per se. It's actually a safety guard sort of done afterwards.
It's kind of like what your mom should have done to you, so that you just find it.
Yes.
So a couple of questions building on the previous ones that just were asked. So this is interesting. I think the answer is you can't, but the question is, wait, how can we be certain the student hasn't just learned?
You can.
Yeah, I thought that was the answer.
You can. I mean, okay. There's unlike with many generative AI things where there's not a clear evaluation metric for similarity, there is when it comes to plagiarism. Like you can say there is 100% certainty this is the same thing. The statistical chance of you writing the exact same text verbatim for 3 pages is, it's more likely that, I don't know, we get struck by lightning 10 times in a row, right? It's just impossible. So.
And the person who asked about ChatGPT said, could you talk then a bit about the role of pre-trained models? What are they used for and how?
Sure. I'll be very brief because I have a lot of slides to get through in about 3 minutes. But in brief, pre-training is there to teach a model how to speak, how to understand language and the context and the semantics behind the words and how they correlate to each other. For example, if something trained on Wikipedia, it would probably learn that the word or the phrase World War II is heavily related to Winston Churchill. Right. That's what pre-training is for. Fine-tuning, which comes afterwards, is how you specialize into a specific task. Okay, I'm going to fly through this next section.
And I won't interrupt you.
No, I'm sorry. There's a lot of interesting stuff here. Okay, we saw a lot of this yesterday. Okay, let's talk about GANs a little bit. We've talked a lot about LLMs, and you get a gist of how the models work. There's a bit more complexity to it, but everybody who's managed to follow that along there today has a good understanding of the basis of how LLMs function generally. Of course, there's a lot of different models and different experiences, but that's a general insight how LLMs work. So GANs, which are generative adversarial networks, are different. These are the purpose of these is they are really to create images mostly. They consist of 2 components: a generator, which creates new data instances, and a discriminator, which evaluates the authenticity of the generated data. you're starting to see this theme of predict something, see how good it actually is, and compare it to some sort of evaluation metric. That's a common theme across most of these, right? Even in reinforcement learning, there's something that repeatedly tells the agent you're right or you're wrong. Supervised learning is you can repeatedly see, the labeled data, whether you're right or whether you're wrong. Right? And with clustering, it's a simple metric like how close are we to finding the right things? How close are things to each other, right? It's still some sort of prediction. Unlike transformer models, GANs are different because they're used to create new synthetic data that mimics distribution of input data, whereas transformer models learn to transfer input data into useful output based on the patterns and structures they learn from input data. So these work by, first of all, creating random data or noise. The discriminator then evaluates this data. If it can't distinguish the generated data from the real data, then the generator's done a good job. Right? That's the evaluation. That looks pretty similar to what I would expect, so good job, you're done. Random data probably isn't going to be accurate, so it has to iterate over. This continues again and again until it produces something convincing enough to fill the discriminator. Okay, let's not go into any extreme detail here. So we have this prompt, Ann Arbor and fall. This is literally from Midjourney, by the way. This is the same image I showed yesterday, but this is how it was generated along the way. I quickly saved images as it was generating. So it first of all gets this, it converts into a latent space, which is just a bunch of numbers really that represent the idea behind the concepts, right? So the word fall might have representations of orange and leaves. Ann Arbor has certain representations of buildings made of brick or whatever it decides. It passes this into the generator. The generator first puts together this idea of some random pixels that doesn't really have much sense behind it. It does have a lot of orange though, so that's not bad, right? It's not terrible for fall. The discriminator then says that's a poor fit. Retry. Try again. So okay, so it tries again. And you see this is starting to look more like it. You can start, I don't know whether you guys can see this, but this looks kind of like a forest. There's some sunshine here. There's a blue sky, right? You can get a kind of feel for what it's trying to do here. So it's clearly starting to edge in the right direction towards this concept of Ann Arbor and fall. And eventually it gets to this. So Midjourney provides you 4 images to play with, right? And that's what the 4 images it produced are. And it kindly says, yeah, that's good enough that we will submit this. This now meets that evaluation metric. This repeatedly generating thing has produced a good enough example. I will say, yeah, okay, you can now show that. And because I just love the art, I want to show it once more. So I told it to save number 4, and that's what I did. So this was originally that random clump. Let's go back just so you see it again. That's this. It's what the palette is started with. I want you to think of somebody who's doing a painting. What do they do at the very start? Here's going to be a face, or here's some trees, right? And then they add more detail. You don't just do a small corner and make it perfectly detailed and then work out. You do it a little bit at a time, build the layers. And it's really quite amazing. This is so similar to how humans do it. And that's how GANs work, general adversarial networks. Okay. Do we have time for a couple of minutes?
We have the time you have. People may have to go if you do.
This is recorded, so if you can't see the whole thing.
And would you share your slides with us?
Absolutely.
Yeah, so we'll also have the slide share.
Okay. So let's talk about its general AI, generative AI's purposes and research, what it can actually do. Because we talked a lot about the technical background. We've talked about the different types that exist. I didn't even touch on video, by the way, or audio. There are still a lot more to this field. So please feel free to look into any of that yourself if you're particularly interested, and ask ChatGPT to what I love to do is say, explain it like a 5-year-old, explain it for a 15-year-old, then explain it to somebody who's like an undergrad, and then somebody with a PhD. And any concept, I'll just read through it in order. I'm like, okay, now I get it. Right? I love that. Okay, so the functional purpose of Gen AI is to, well, one of the many purposes is for data augmentation synthesis. So you may want to generate a bunch of data that represents existing data. Today, I talked to some medical experts who said that they have fairly rare diseases. There's some information about them out there, some data about them out there, but they can't, if there's only 6 patients in the database, how are you supposed to study that data, right? It's really hard because it might be very particular. Maybe they have very little in common. You can't identify the same symptoms. So what do? You feed it to a generative AI model, it'll extract those key features, and theoretically you can produce a larger data set that represents the same core ideas, and you can study that data set. Same with surveys. If you do a survey of 50 people, you could then pass it into generative AI. It learns the concepts and idea of those studies, And the surveys will produce 500, 5,000, wherever you need. That doesn't mean that this is always ethical and right or accurate. They can do it, is my point. Data imputation is not a new field. In genomic prediction, when you extract the DNA from somebody or something, it's really expensive. Back in the year 2000, it cost tens of millions of dollars to have the first ever DNA, the human genome actually built. Do you guys remember that? I don't know if you're old enough, old as I am. I remember when this was massive news. They said, we have finally indexed the whole of the human genome. Big deal. This was a huge thing, and it cost millions of dollars. 23andMe is the popular website now, right? How much is that? Like $8? Right, it's incredible. You can send off, you get a little saliva spit test, you send it off, and they will scan your DNA and tell you your heritage, or what it actually does is tell you where people who have similar DNA live now. It doesn't mean heritage, it means where those people live now. So displacement is very much ignored with these kind of things. That's my genomic background talking. But these data sets are expensive they're still expensive to gather. So what they did back in the day is they would get, 1% of the data, and they know that they have 100% of the data somewhere. So they just compare the differences. And they say, well, we can guess the rest. And it turns out we can get really high accuracy. We can get like 90-something% accuracy of it being a similar thing. So it saves a lot of money. And if you're running some preliminary tests, imputing like that is a great way of doing it. And this is not new by any means, but with Gen AI, there's these additional layers of depth to be explored. It can potentially find the more key features in a data set that might not be found through traditional statistical methods. Design and prototyping. So if you want to generate new designs for experiments, like you could say, for example, I have this idea for a research program I want to do. What's the best way to do it? And it would say, oh, well, you could try this. And then you could say, well, I want to be more energy efficient. So what's another way to do it? And it could provide you a more efficient means of doing the same experiment, this kind of experimental design, right? Or prototyping. You could say that I have this idea for some code. How do I actually connect all these various classes and parts of the code together? And it could prototype a general idea for you. Predictive modeling. You could say I have this information I can provide you with past experiences. What do you think is going to happen in the future? This can be done for experimental design again, or even if you finished a study in the past and you say, I'm thinking about going in this direction, what do you think would happen, right? We have this preliminary test done, what could be done in the future? And it can give you an idea of estimating what it thinks might happen, especially if you train it on these kind of data sets. You can have personalized user experiences. So if you train your LLM, for example, on the field that you're a specialist in, it can then provide you very personalized experience when you're using it, because it can say, I see you are a social scientist who specializes in political theory of the 1800s or something, right? And if you pass in all of the papers and all of the information you can about that, and some information about yourself as a scientist and what you're interested in, it can provide that really nice personalized experience that's really useful for research. There's, of course, creativity. It comes with new ideas and new concepts and new ways of doing things in general across science. Autonomous actions and automation, including the obvious things like literature reviews, summarizing text, data pre-processing, code testing, data analysis, visualization, generation, knowledge extraction from unstructured data such as text, and early stage peer review. Right? That's touching. That's like the basics, right? That's before you start integrating AI into your own models. Here are some examples of LLMs in research. This is, in fact, let me skip over to this one here. In the social sciences in particular, I had to think about this. I'm not a social scientist, but I had to think about the things it could be used for. I thought this would be I think Gen AI could be used for where original data is limited or sensitive. If you have some social data that's people are afraid to share or privacy concerns, you could generate new data based on those existing that have the same sort of features come out. It might be something you can actually share, right? So it'll store those key features, those key patterns in the data set without actually telling anybody about demographic information or personal information. You could generate synthetic populations of countries and try out new ideas of legislation, what to do, what political opinions of people could be, what their thoughts on religion are. If we had a different type of America that was formed from different countries back in the day, what would it look like? These kind of questions you could potentially generate and try and ask questions about. virtual scenarios and dialogues or social experiments where the AI system can mimic human interaction. Right? These are all the possibilities. Again, these all have their own ethical and legal implications that would absolutely have to be considered first. But it's something that there's a lot of potential, I think. So, in conclusion, a lot of the underlying technology is not new. The computational power has unlocked these underlying capabilities, allowing us to do generative AI. Gen AI can help with a variety of tasks for researchers to be integrated into existing models. So if you have a machine learning model that can do something, you can make a generative AI based on this, or as a sort of curator or an agent representing that data set and ask questions of it on your behalf. What would this look like if we generated 3 years later? What would it look like if we plotted this? These kind of things. Learning with Gen AI can help you create your own custom models. Right? All the things we've been talking about are these existing models that already exist out there: ChatGPT, Bard, Llama 2, and all these. But you can make your own, and you can take these existing models and customize them for your data sets. And you can have true novelty in your research, but have the power of these models being trained on your specific niche data set. That doesn't exist out there. That's a brand new thing. But while it's very powerful, these must be trained on carefully structured, carefully considered data, because it's very easy for these things to pick up patterns that are common human behavior, like prejudice. So you need to be very, very careful when you think, and there's hundreds of papers and courses on that specific topic. Please read more on it before you just throw a data set together and pass it in, right? Because it will have unintended consequences. We also talk about transformer models and GANs. These are some of the most commonly used techniques in generative AI to generate content based on a training set. They are quite complex things. I try to give a brief overview of how these things function based on what I think most people know from stats. But if you didn't follow everything, don't worry. There's a lot of information today. I hope you can watch the recording and pull out the information you need and look up the additional resources to help you with that as well. So thank you for your time.
Thank you, we'll have we have lots of questions, and Ken will hang around, but we also have folks who need to go, and as you need to go ahead. And I'll start us off. There was a question here from the chat. It says, given that DNNs can have millions of nodes, I'd like to know what's the state of the field in terms of getting at inference or about the association between particular predictors or inputs in the outputs.
I would say it's a field of study, right? I mean, this is, especially when it comes to inference, it's a hard thing to answer because it is an active field of research, right? Exactly getting these inferences and these designing a neural network of any kind, especially deep learning, when it has so many millions of nodes, and then potentially that search space of trying different number of layers, different number of neurons, it's incredible, right? Then you can change your activation functions and your learning rates and so on, right? There's so many things you can try differently. I would say we barely scratched the surface on answering that question. And this is the really scary thing about any of these modern artificial intelligence systems that we have. They're not interpretable. I can't tell you why it's come to some certain decision, right? Traditional stats has more insight into these things, but we're not good at it yet. And if you have any ideas, please put them into.
Yeah. So it is an active, and of course you can see why it would be a direct interest to the scientists that prediction's an awesome thing, and it's one of the things we want to do. But we'd also like to know how did it get to that prediction so that we can use it in some other context, maybe where we don't have mountains of data yet to try to apply it.
I can also say that there are means by which you can inspect a model that already exists. You can look at those individual weightings of the individual neurons and trace it back. It's just a very lengthy and difficult process. And then you have to think about how it was trained in the first place as well, not just the answer it gave, right? Right. So it is possible, but it's incredibly difficult.
Any questions from the audience we want to take?
Yeah. I kind of have a silly question. Do you think AI could ever like replace like humans, like researchers? Like if it can come up with like research ideas, and it definitely has the better statistical.
No, I think that's a great question. It's something we're all afraid of, right? Okay, there's the scientific and there's also the poetic answer, right? scientifically, I think a lot of people are short-sighted and they talk about this year right now. I think 3 years ago, we wouldn't have seen ChatGPT coming a mile off. We would have said it's 20 years, 30 years in the future. So we've already got automation that replaces people in jobs. So yes, it's absolutely going to happen one day where there is AI that will do most things, right? I see that as a person in the future. I think from a scientific perspective, that I don't think we're just going to cut off here and say we're done. I think we've barely started. Exactly how far we go, I don't know. Because I think, again, if you asked 20, 30 years ago, what will AI do? We would have said, well, it can't be creative. It can't possibly be creative. It can only do logical things because computers are basically calculators. And then today I'm showing you these paintings put together in 6 seconds that are beautiful and gorgeous and meld together these unique concepts into true novelty and true art, in my opinion. So in 20 years' time, I don't know. All I can say is the best thing that we can do right now is learn AI. All of us have some kind of insight because it's a tool that we'll all have to use. And those who don't know how to use AI are the ones who struggle with their jobs, in my opinion.
Well, that's cheerful news. But yeah, you might be inclined, I might have been inclined to say, well, we'll still come up with the questions, but actually you could ask the generative AI, what's the next question I ought to ask?
Yeah.
Right. So, terrific. Anything else? Well, yeah, here we go. So there are many, many resources out there now. This is a good one to end on. What are your top recommendations for where to go to begin learning?
I'm going to take this as an opportunity to plug. I work for MIDAS, the Michigan Institute for Data Science, and we put together a quick guide. I mentioned yesterday, we put together a quick guide on how to use generative AI. We put together a resource hub that has some of the top models and top research papers and top places that you can go and play with generative AI yourself. The first place that I would check, especially as we're all affiliated with the University of Michigan, check out what we have here at the University of Michigan. We have specific courses dedicated to this. We have new resources being put together. All day today, I was talking with faculty from dozens of different schools at a different workshop on how we're going to be implementing generative AI into research and somewhat to teaching as well. This is an active thing that we all care about. So we're all pulling together these resources that are most useful and applicable to us. So check out the MIDAS website first. We've got a whole generative AI section there, lots of useful information, including training. It tells you it's external, so it's not just a personal plug. It'll say, go check out the Stanford course, go check out this Google course. It has academic and industry-based solutions. So that would be my first place to recommend. Otherwise, YouTube's a fantastic resource. Who doesn't like watching these videos to explain things from basic to intermediate to advanced? And there's also lectures like these there. So check all those out.
Thank you very much. We'll call it a day. But Ken, you have one more question on the chat that you can type in and answer. But thank you, everyone.